Dear students, I have some inspiring words for you. It is rare to be born as a human being. It is still more rarer to be born without any deformity. Even if you are born without any deformity, it is rare to acquire knowledge and education. Even if one could acquire knowledge and education, it is still rare to offer service to mankind and contemplate on higher self. If one leads such a selfless divine life, the gates of heaven open to great such an evolved soul. Thank you. Dear students, I have a new video for you on atomic structure. So please go through it and share your views. Okay, students, today we will discuss the atomic structure part 2 in chemistry. So, we have gone through the earlier concepts about the atom. Now, in this head, we will discuss about the concept of spectrum or spectra, importance and limitations of Bohr theory, and the dual nature of electron or the matter waves, the photoelectric effect, Heisenberg uncertainty principle, and the orbit and orbitals. So, firstly, about the line spectra of atoms. What is line spectrum? Whenever a material, substance or element is heated at a very high temperature or anyhow by carrying out some electric spark or by other means, when the substance is heated to a very high temperature so that it starts to emit light, and when this emitted light is allowed to fall or to pass through a prism, then the light or the radiations obtained is split into a pattern of different colors of light. That pattern is known as spectra or spectrum. The singular is spectrum and plural is spectrum. The line spectrum, or particularly the line spectrum of emission, is related to the atomic state of the matter. At very high temperature in vapor phase, when substance comes in atomic state and light or radiations are emitted by it, then the spectrum so obtained is found in the form of fine colored lines. That is known as line spectrum. So line spectrum is characteristic of atomic state of the matter. Line spectra are like atomic fingerprints. We can say that the line spectrum is DNA of a substance or a matter or an element. Forensic scientists use line spectra to identify the substance. So this is all about line spectra of the substance, and particularly as we have gone through that the line spectra is related to the atomic state of the matter. Now in this context we have to discuss the series of hydrogen spectrum. When in vapor phase state, or when the hydrogen gas in a chamber is heated to a very high temperature, or an electric discharge is carried out in an atmosphere of hydrogen, then we obtain the light or the radiations. These radiations are allowed to pass through a prism, and the beautiful pattern of colored light is obtained. Now in hydrogen spectrum we have number of series, and these 5 series are the forms of spectra in hydrogen spectrum. So here the first series which was observed by Bohr, it is a visible series of hydrogen spectrum, because the radiations in this series fall in visible region of light. So that is known as Bohr series. And when in hydrogen atom the electrons from its excited state from higher energy levels comes back to n equal to 2 energy level, it is going to produce that type of series or light or radiation which fall under visible region of light. But the first one series is Lyman series. Whenever hydrogen atom in its excited state, the electrons from higher energy level fall to the ground level, or they come back to the ground level, that is n is equal to 1. The radiation emitted, these are invisible, and these fall in ultraviolet region, that is called Lyman series. The third one is Paschen series, and the fourth one is bracket series, and fifth one is Fund series. In Paschen series, electrons from higher energy level or in excited state, they come back to n equal to 3 energy level. And in bracket series, the emission spectrum that is further it lie in infrared region, and the excited electrons come back to n equal to 4, and in Fund series they come back to n equal to 5. So the four series is, that is Lyman series, Paschen series, bracket series and Fund series. These radiations are invisible. Paschen, bracket, Fund, these three series, the radiations fall in infrared region, whereas the Lyman series fall in ultraviolet region, and the only visible radiations or the series, it is the Bohr series, and that is the reason that first observed series was Bohr series. So here it is the pattern of hydrogen spectrum. Now spectral lines in hydrogen spectrum, we have a basic formula to find out how many number of lines can be obtained in a particular series, that is number of spectral lines is equal to n into n minus 1 divided by 2. Suppose the radiations or the transition of electron is taking from n equal to 4 to the ground energy levels or lower energy levels, then the number of spectral lines will be obtained equal to 4 into 4 minus 1 divided by 2, that is 4 into 3 divided by 2 is equal to 6. So where n is the cell number from where the transition of electron is taking place. Now here are the 5 series: Lyman series, Bohr series, Paschen series, bracket series and Fund series. And for these series, the ground energy levels on which the transition of electron is taking place, that is 1, 2, 3, 4, 5 respectively, and the higher energy levels, these are for Lyman series, that is 2, 3, 4, 5 up to infinite, that series fall inside ultraviolet region. For Bohr series, the higher energy levels from where the transition of electron is taking place, these are 3, 4, 5 and that lie in visible region. For Paschen series, the higher energy levels from where the transition of electron is taking place, these are 4, 5, 6 and that fall in infrared region. Similarly for bracket series, the higher energy levels are 5, 6, 7, 8 and these fall inside infrared region. And for Fund series, it is 6, 7, 8 up to infinite and that is also falling inside the infrared region. Now wavelength and wave number in transition can be obtained or can be demonstrated by number of series, that is the wavelength or the wave number. The formula for wave number, it is, as we know, that wave number is the reciprocal of wavelength, and that 1 over lambda is given as nu bar, and which is equal to Rz into z square into 1 upon ni square minus 1 upon nf square. Ni is the initial energy level number and nf, it is the final energy level number. Z is atomic number and Rh is Rydberg constant. The wavelength of radiations in different series, we have a chart here that in Lyman series the wavelength starts from 91 nanometer to 122 nanometer. In Bohr series it starts from 365 nanometer to 656 nanometer, And in Paschen series, the wavelength of radiation is found from 822 nanometer to 1875 nanometer. The Bohr model was successful in determining where all the spectral lines of hydrogen should be. Bohr successfully explained the spectrum related to hydrogen atom, but rather Bohr model failed completely to explain the spectrum obtained of the elements of the elements having more than one electrons. That is, it failed to explain the spectrum related to multi-electron atoms or multi-electron elements. Now, RH, the Rydberg constant, is equal to, by the calculation, it is 2 pi square into e raised to power 4 or into m into k square divided by c into h cube, where pi, that is equal to 22 upon 7, e is electronic charge, that is E is equal to 1.6 into 10 raised to power minus 19 coulomb. M is the mass of electron, that is 9.1 into 10 raised to power minus 31 kg. K is a constant in Coulomb's law, and its value is 9 into 10 raised to power 9. C is the velocity of light, which is equal to 3 into 10 raised to power 8 meter per second. And H is Planck constant, and its value is 6.6 into 10 raised to power minus 34 joule into second. So here RH, the value of Rydberg constant for hydrogen atom, on calculating it comes out 1.097 into 10 raised to power 7 per meter. Here is the illustrative problem now. A gas sample of hydrogen atoms are shot with electrons of 12.75 electron volt energy. What will be the energy of radiation emitted in Bohr series? So here we have an electron which possesses an energy equal to 12.75 electron volt. It is fired in a gas, in hydrogen gas. So that energy is going to transfer that electron to some electron in its or that is going to penetrate or inside the hydrogen atom. So up to what energy level it is going to reach, that can be obtained here. So here energy of an electron in ground state, we know it is minus 13.6 electron volt in hydrogen atom. Energy of excited electron, what will be the energy of excited electron? Energy imparted is 12.75, and the energy that goes in ground state, that is minus 13.6. So the energy in excited state of electron will be 12.75 plus minus 13.6, that comes out minus 0.85 electron volt. Now for hydrogen atom, we know that En, that is the energy of electron in nth energy cell, is equal to minus 13.6 into Z square divided by N square. So here we have to find out N, and substituting the value Z equal to 1, and N square comes out approximately 16, so N is equal to 4. That is, the excited energy level is N equal to 4. So by supplying 12.75 electron volt energy, the electron is going to get the excited state N is equal to 4. Now it is coming back to N equal to 2 for finding out the radiation emitted in Bohr series. So Ni is equal to 2. Now the electron in excited state that is N2 is equal to 4. So energy is equal to minus 13.6 into Z square into 1 upon n1 square minus 1 upon n2 square. So that is minus, that is equal to delta E, that is minus 13.6 into 1 square into divided by into 1 by 2 square minus 1 by 4 square. So that comes out to minus 2.55 electron volt. So that is the energy emitted in Balmer series. Now next is drawbacks of Bohr model. Though Bohr model was quite successful about the hydrogen atom and it could successfully explained the spectrum related to hydrogen atom, that is the elements having only one electron in their outer shell. So uh, that model explained the spectrum related to hydrogen atom, but Bohr model quite completely failed to explain the Stark effect and the Zeeman effect. What is a Stark effect? When electrostatic field is applied on spectral lines, that is the spectral lines are allowed to pass through the electrostatic field, then it is found that each spectral line splits into two. That is known as Stark effect. And similarly, Niels Bohr model failed to explain the Zeeman effect. What is in Zeeman effect? When the spectral lines are viewed under magnetic field, then what happens? Then that these spectral lines split into number of fine spectral lines. So this type of spectrum so obtained, it is also known as fine structure. Niels Bohr model quite completely failed to explain the fine structure of atom or fine structure spectrum of the atom. In Niels Bohr model, it was one of the postulation that the electron revolving in nth orbit will have its angular momentum as nh. It is equal to integral multiple of h upon 2 pi, that is in nth orbit it is nh upon 2 pi. But he could not explain that why the quantization of angular momentum has been taken. Now the third one is that it explains only the spectrum related to hydrogen like species, that is having single electron in their outermost orbit. But in case of an atom or element having more than one electron in outermost orbit or more multi-electron atoms, it completely failed to explain the spectrum related to it. Now, Bohr's model also failed to explain the dual nature of the matter, that is, a material particle can behave as a particle as well as wave, and also it has no concept or no proof about the Heisenberg uncertainty principle. So, means Niels Bohr model needed some type of changes or the postulations or some corrections. Now we will discuss the dual nature of the matter. De Broglie first of all proposed that the fast moving particles or materialistic particles can behave as a particle as well as wave. So that type of nature of matter is known as dual nature, and these type of waves related to a moving body or materialistic particle, these are known as matter waves. According to Planck's quantum theory, we know that the radiation energy either being absorbed or emitted, it is always found in the integral multiple of h nu, that is where E is the energy and H is Planck constant, and nu it is the frequency of radiation. So that is equal to h nu. Here, according to Einstein energy mass relation, we know that it is equal to mc square, where E is the energy, m is the mass of the substance undergoes destruction, c is the velocity of light. Now, on equating these two, we have mc square is equal to h nu, or mc square is equal to h into c upon lambda, where nu equal to c upon lambda. So here lambda is equal to h upon mc. That is, here mc is the momentum of photon and h is Planck constant. De Broglie related this formula to the matter waves also, and he stated that for any materialistic particle which is moving with velocity v having mass m, then the matter wave related to its wavelength is given as lambda is equal to mv. So this is the concept about the matter waves. Now here we have a problem, illustrated problem. The speed of 200-gram golf ball is 5 meter per hour, very slowly. It is moving. The wavelength of the ball will be of the order of number 1 10 raised to power minus 10 meter, number 2 10 raised to power minus 20 meter, number 3 10 raised to power minus 40 meter, number 4 10 raised to power minus 30 meters. So here, using by de Broglie equation, we have wavelength lambda is equal to h upon mv, and h is 6.6 into 10 raised to power minus 34. Changing mass into kilogram and changing the velocity in meter per hour into meter per second. So we have here multiplied by 3600 divided by 0.2 into 5, and that comes out 2.385 into 10 raised to power minus 30 meters. So here it is of the order of 10 raised to power minus 30 meter, and that is it is of the order of 10 raised to power minus 30 meter. So here that is answer number D is correct.